Okay, so continuing our discussion earlier, okay, so remember we have this portal frame in Staad that we loaded with a harmonic load by defining a time history as harmonic load, harmonic force. Okay, so for example, we have 2 cycles per second. It's a harmonic function sine and with an amplitude of 40 kilonewton. So meaning our F is 40 sine omega bar t. Yeah. So wherein omega bar is 2 cycle per seconds. Okay. Yeah. And since we already know the period of this from the lecture, it's about 0.08 seconds. And applying this time history definition here, okay, and then analyzing it, we have the resulting time history response displacement as this. Okay, so you will notice that we have a peak deformation of 1.77 millimeters at 0.14 seconds. And also almost the same or 1.79 millimeters at 0.36 seconds. So that's the maximum deformation of our single degree of freedom problem with an applied loading harmonic force of 40 sine omega bar t. Okay, so let's try to solve this manually. Uh, remember, during our derivation, we were able to come up with a response. Okay, we got this, we derived that, and combining the homogeneous solution and the particular solution, and then finding the value of C1 because we know that C2 is equal to 0 here. Okay, so substituting C1 in this assumed solution, the final uh, uh, response, no, or u of t, or the response with respect to time is this, which is again a function of the static deflection, P over K, and then the frequency ratio. Frequency ratio or the omega bar of the applied force and the natural frequency of our system. Okay? Okay. So we will use that formula to get the response here. So using that and applying here, okay, after typing in this formula, so and starting from 0 up to about 0.39 seconds. So this is the time history response of our system. So of course, we also have the same period of 0.08 second as we got in Staad. And okay, with a static deflection of 1.6. Okay, because we have this K and we have this force. So this over this is this, or 1.6 millimeters. Okay. Now, you will observe that the maximum deflection is about here, 1.7. Okay, so where's that? And this one, if I move, uh, by the way, omega bar is this because 2 cycles per second corresponds to omega bar is 2 cycles per second. So 1 cycle is 2 pi rad, right? 2 pi per second. So multiply that, you will get 12.5664. 12.5664. So that's why uh, if you look at the formula, using this formula and with a given omega bar 12.5664 and the natural frequency of the system of 78.7902, then you will have this time history response of our 0.08 second structure. Okay. If you will realize 0.08 is relatively a rigid structure, no? 0.08. That's why the 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 dynamic amplification is a bit small because from 1.6 static deflection we got about how much? 1.8. So as you see, that's only 1.8 millimeters. Okay, so 1.8. So if as you see, this is also almost 1.8 also. Take note of the time, the maximum peak response occurs also at 0.34, while here is about, you check, 0.34 and 0.14, right? 0.34, 0.14, which is almost the same with what we got in Staad. Okay, 0.14, 0.34, and then the maximum response is also the same, almost 1.8, 1.7, right? So here is also 1.7, okay, 1.8. So meaning what we got here in Staad is almost the same as what we got here in our spreadsheet by using this formula that we just derived. Okay, so that's a time history response. And yeah, so you will observe that uh, if you also plot the harmonic force, this is the harmonic force is almost the same. We have also almost the same cycle, meaning since the structure is relatively stiff, no? It's relatively stiff. Okay, so the effect of the lateral force, the harmonic force, is not much, no? So the behavior of the structure during its lateral deformation is almost the same with how the cyclic lateral force is behaving. Okay, so that's how we were able to implement in Staad a simple single degree of freedom uh, force vibration, no? Force harmonic force vibration. Okay. Now, uh, I'd like to also show how we were able to do that in our spreadsheet using numerical methods approach, using NEwmark's data. So this is the same spreadsheet that we used earlier. So we have 0.08 second also as a period, and this time the delta t is also 0.01. This is the mass and the stiffness to come up with a 0.08 second period and a frequency of 78.79. And looking at our spreadsheet. So this is, again, this is time history response. So if I click on our time history response, it's almost the same, right? So we also got the peak deformation at about 0.15, no? Having a peak deformation of 0.18, which is almost the same with what we got in Staad, 1.77 mm and also 1.8 mm. And how about on the negative region? It's almost the same. At about 0.36 seconds, we got 1.8 millimeters, and the same with what we got in Staad. Okay, so that shows that you can use the manual calculation using a closed formula or using uh, a closed form formula that we just derived by differential equation, or you can use a numerical methods approach using NEwmark average acceleration method, and also implement that in Staad if you're wanted to, if you're about to model a more complicated structure. Okay, so you have lots of option in verifying the response of your structure. But again, uh, if you have a, if you are about to solve a general dynamic loading, this NEwmark data approach, a numerical method, is of course the preferred one, which is also the same for sure is implemented in the software like Staad. Okay. Okay, so this is the actual time history response of this 0.08 second structure. Okay, peer at time 0.10. Okay, now remember, since our peak is 0.14, let's try to adjust that. Okay, so that's the peak response or peak deformation at about 0.14 seconds. Okay, and this is the period 0.08 seconds.